Vaya, no, pero me dice que un día de
So basically, let's continue. What like basically the one was I. So I got this kind of thing here, but I was doing, but this gimme stuff. So that's why I'm liking Kimi. Kimi's giving me all I need, literally, of it. I mean, it's kind of like upsetting to see people don't really people love this kind of thing. I love quantum physics too, but I'm not like I'm doing it wrong. I'm doing it my way. Everyone's trying to do it that way. That's what I'm saying. It's not really a bad thing to not know what you're doing. It's just about to try to give up without actually putting an FIA in. That's what I'm saying. It doesn't. Hope I'm right with about a cathode. Cathode. I'm gonna try to go find a cathode on the internet. Cathode. I'm gonna scale the cathode. What cathode? Cathodes are polycharged ions. Are they ionic? Cathode. Cathode is an electrode. But is it polar charge? Electrode is a covalent charge which leaves a polar. So the cathode is a negative charge, positive charge. This polarization device. But is it have a copper cathode? Graph to this battery. So this is a battery. The cathode is anode. Oh, this one's saying. I know the color, basically. I don't. Electricity. Doing for me, my mind, really. Okay, now I'm streaming again. Let's close the games. The claims are closed and everything else is closing because I got started stream. But I just got started properly. I got 31 minutes to do it, but I don't know timeout for the 5 minutes. This is what I'm saying. I got my calculator cleared. I'm starting the stream. The time is now cleared. But I gotta do it properly because I'm doing it properly. So, what am I really doing? I don't really know, but I'm right about this. I'm doing. It's like a. Okay. So literally, I'm just trying to do it properly. But what was I measuring before? I don't really know. Basically, key physical. This is what I'm saying. I just need this one. DP. I just don't like one wasting time, but it's not really a bad thing per se. It's a terrible thing because it's like no. That's why, guys. I'm just trying to set up my stream again because I'm trying to start my tabs. But I'm not really gonna be bothering with kind of. I'm doing the hard work by labor, but I'm not doing for you can do for me. So it should just come up now in the kind of interface here. Because it should be here. The code is symbolic. Basically, this is a new conversation. No, this is not just a whole conversation.
ভালো হয়েছে আস্তে আস্তে দাও উড়াতাড়া করতে হবে এই লোকাল উড়াতাড়া করে মারাতে গিয়া দূরই আস্তে আস্তে দাও
So basically, basically, I'm gonna put my screen on. So, this is what I'm saying. So, we got like Kimi. Okay, so he's giving me some stuff like I don't even like Kimi AI to do it. Basically, I got this kind of definition here. Kimi just didn't stress me with it, but I just put a thing in and Kimi just told me one screw back. I'm just recording myself again. Okay. So basically, this is what I'm saying about. She used the Gaussian. So the Boy's law is just literally just the problem of the thing I'm saying. I'm gonna give you the model of it, but I don't wanna give you the wrong model. But I'm gonna give you the right model of this. You see this thing, the animation showing the relation between the pressure and volume when a mass. No, this is wrong, guys. This is wrong model. I don't like it. Namely, this is wrong model, guys. this shows the mass. Today's date is 8th of December 25. The night time is 9 35 p.m. So you get the mass. The mass is being pressured down. So the volume increases and the area. This is wrong. This is wrong measurement. This is the wrong measurement. This is very wrong. So this one I'm saying is a piston. A piston is what? Piston what? You got a piston. What's a tungsten? I don't know. Oh, tungsten steel. A piston. A piston pushes, but what? Weight carries. Weight carries. This is just the problem here. Pressure and temperature. This obviously this is not the right amount. So the pressure is the piston. Then that pushes. Let's say push and pull. It's a push and pull. For the system weight. It's not a push and pull. The piston is just the kind of homework. It's just a system reason. So I'm gonna give you that to go by because you guys are understanding this from me. So I'm not. So you got a piston. A piston is what? This is the piston. A piston is a circle. This one, this is like a piston. But this is the piston, a push and pull. This is what it does. It just push and pull. It's lever. So you can get two types. So this piece of piston, internal combustion engine. A piston what? It's a component of reciprocating energy. Pump. A push and pull. It's like it just does one thing and does it perfectly. It has to do it perfectly. That's good. It doesn't matter what it's a power system because it doesn't think about it knows about its state. It works on the inversion. It pushes and pulls. It pulls and pushes. The volume will start can start with a push or pull. That's what it is. What can you put? This is like so you can get a gas compressor, but this is a gas compressor. You push the gas, but the compressor has to push gas some way to get some volume. This is a hydraulic cylinder, but it's a compressor. So the thing about the piston is like it's push and pull. We get the tungsten, which I'm thinking of tungsten. I don't even know what tungsten is, but I think it's related to a piston. So just search it up. Tungsten. Still tungsten cube. Tungsten is a no. This is a metal. No, something about. But basically, this is metal, but it's which is tungsten. You can push tungsten. You get the tungsten. Basically, let's go to the 1 This one. So your piston is what pushes. So the piston is like weight. So what is 1 kilo or 1 kilo? Let's do this actually. Let's use tungsten actually, because we get tungsten kilograms of tungsten. Let's just do this actually. Let's do it properly. Piston because the tungsten is iron, so we use tungsten. Tungsten. Let me just do it because I use piston. Tungsten. I'm going to 1 kg of tungsten. That's how much. How much is that? 1 kg of tungsten as well. Basically, this is my look at the price. Just with tungsten still. 1 kg of tungsten. To piston. And 1 kg to piston. 1 kg piston. So you think about this thing. The phrase 1 page is basically this is a tungsten still. But look at basically how much can you buy one piston? Can you buy one? No. Basically, I'm looking at the size. Okay. So if you have, I'm saying literally, you get a calculator. Or calculate dimension of the unit. So if you have a piston that's 1 kg, 1 kilogram, you have the same thing that this does one thing: push and pull, push and pull, push and pull, and push or pull, and get the weight. The weight is the piston. So the piston weight, what the piston is pushing and pulling, the tungsten. The tungsten is the iron ore, the kind of mineral you push and pull. When you go switch, you can think of the tungsten ore. You can think of it where you've been processed. You can think of it, if you're gonna process some ore, I gotta make the ore So the tungsten is like the metal you're compressing or decompressing. So you're pushing and pulling the tungsten. Just pushing something. That's what you think about. You don't think about space and time. Think of it as dimensions. So the sheer one state of dimension. So if there's a push and pull, there's a push and some push on them. But if the piston pushes something, so the pressure, the force of a calculator, piston force calculator. Because yes, basically PCI. It would be basically this is a piston force. So the bore diameter. Basically, this is piston pipe. Basically, you see, this is the bore. So you got the bore area, the bore cylinder, but the piston force is same. So let's calculate bore diameter. The diameter is 12. The bore area is 12.5. Let's do 10. Let's do 15 because I love this kind of pi numbers. 15 cylinder pressure PSI. Basically, just squeeze how much you push the system. But it's kind of scary. The PSI is the standard scale for pushing stuff. The piston, but the piston is just a scientific device for compressing them. But when there's under pressure, what do you do? Because piston is just a measure of space and time in that system. So this is a PSI scale. Pounds per square. I mean, how many pounds per? Okay, good stand is power per square inch, and just a PSI. It's like literally I don't know these people. Pounds is 12. Let's get 6. Let's get half of. Let's get 5, 10, 10, 10. 10. We can get 5 minimum because there's no change. Because if you measure 5, that's we got nothing in terms of scale. But this one has the equivalent to the tensor model. So this model, the boy, gotta get equivalent. So the bore diameter of a frame gives you the bore area of 17.6 17.6 meters millimeters squared square millimeters or square millimeters but in centimeters in centimeters of B 1.767 bore area. It covers is this direction. Basically, it's the force acting itself, but you have the ability space and time. But this is force and weight. Basically, I just the problem of the problem. Basically, get the newtons. So you get 6.089 newtons or kilonewtons is what pound newtons. You get pound force. Basically, this one I don't really need. This one is the one Americans use. 1.3695 both force. But the pound force is the newtons equivalent of 6.08. Like this so really this psi is a pressure dynamic. It's the dimension of the all shear. But if you think of it this way, if you think of a teleport, I'm gonna give it to you guys a teleporting. But you go to left state the all share. For example, you get two characteristics all share, and then you one right axis. They have one left. They share two left axis. They have to share two left axes. What I mean by that, you have to double the force you use twice. For example, if you have two left axes, we're talking about basically going left, north, east, south cube, south times south. That will be south square. South square. This is left axis. Northeast, northeast, south, no. Going west cube. What's the power 4? See, what's the power 4 is actually the share. What I mean is the share two left to one right axis. What this means, whether the pressure or the time is different, the dimensions have a two left rotation. Two left rotation, because literally it's two left rotation. Two left axis. You have to take two axes of rotation. You have to change your view, like your angle, to that problem. For example, left is if you're observing gravity from another dimension, you are being pushed away, pulled away. Basically, if you're the dimension that is how can I put it? Say we have redshift, we are in the dimension, we are observing redshift, we're moving away, but we're pushed away, or even just pushed, or we're just growing. But that means we're being pushed away. We're pushed away from everything that we don't know. So it's growing. It's imploded. So we're growing. We're growing in our own way. We're living. So that's why we get a redshift. But if I'm trying to observe this state and I'm moving away from it, I'm getting red. I'm getting redshift. I'm getting a static wave system. But that means the system is dynamically moving because I'm outside the universe. But that means I'm getting some state that's arbitrary. That's the measure. They can get some noise with it. If I'm moving away from all the things, and I'm moving away from all the things that's everything and nothing, this is a state that's a still like a measure from that state. Measure my own universe. Very quickly. I don't think about this problem, but it's a dimension I can access. Let's talk about it. That's a bit harder for me to as well, but it's just because so I'm saying we go west cube. This just means west times west is one still state that remembers everything and nothing of pressure and volume. Pressure and volume. Because the piston applies pressure and the weight gives volume. So the weight gives mass. Basically, the weight adds on to the dimension of XYZ. While the pressure, but this pressure and weight are mediums. They're not anything else but mediums. Think of it this way: they are just places that you already know of, but you can't observe because you already propagated that wavelength. For example, let me find the kind of standing. So this is a pressure. This is my model here, but basically the shear 45 degrees psi. Basically the shear half a state, the shear half a state, a quarter of a state. But see, this is wrong. This is mass and temperature. So this mass, the mass is not really the problem. It's the temperature that's the ability. The mass is the basically if you measure the mass, you get a temperature. If you measure the mass, you get a temperature. If you measure the temperature, you get a mass. So I'm saying in this model is not really accurate because the mass is not changing. The mass is not changing. The mass here is not growing, but this mass that's actually changing. It doesn't matter. This is not going. Basically, you get volume that's 6. Volume that's 3. You get 6, but it's wrong. Why? Because the pressure is increasing, but the volume is decreasing. So basically, you gotta remember this word is called. What's it called? When pressure this is called a correlation. A correlation. And that's what you gotta know. Correlation. Because it's dimensional, basically. Dimensional work on correlation. So this is just what I'm saying. Dimensionless vectors are correlations. They're not dimensionless. They're just they have the shared inverse state that give that dimension. They're distant. They don't exist together. They never did exist together, and they're different systems. They want to stay different. They're distant states. So they have a correlation. So basically, this person, if the person pushes, if you have a weight carries some. If you have weight, weight has so you have 500 milligrams. So you have 500 kilograms of something, and 500 kilograms, and you have 500 on two axes of weight, two dumbbells. How do you weigh them? Those are a balance of a half and a half. But if this half is what a dimension, this half is one dimension. Basically, the shear extent. So this is the same thing. This weight thing, 500 kilogram. Over basically these two axes of weight. If a force affects a weight, basically, I won't do it properly. So a piston pushes. A piston will push a dimension, but someone will push on. But it's a piston that pushes something. But the pressure is wrong. So this is like a weight. This is an equilibrium of piston. But this is thing that can correlation between two systems. So if you get one as a weight, you get one as a piston. A piston pushes, compresses and decompresses. It just pushes and pulls. But we call it compression. Why I say push and pull is because it's a piston, but it compresses, it forces, it triples, it quadruples the force it does, and that's what's called pressure. Because you don't do anything like serious like that. But if you have some kind of state, you are pressure on a state, on a system, that's what will give into the pressure, and that's what the thing doesn't really matter here. So you get the pressure and the temperature. The pressure and temperature, that's what's wrong about it. It doesn't give the full picture. Because you can always change the pressure by 10% at each interval. Why 10%? So you have a 1,000 kg. 1,000 kg is the same as what? 500 kg. But in pressure, the pressure is like the force action on the object is 500 kg. But that force is like windows together. They get a half, a quarter, plus a quarter. But you get a space-time diagram. This is what you want. Space-time diagram. You get a space-time diagram of pressure. This is what the first one says. So the more space you have, the more volume you have, the more space you have. Let's call it volume. Which I don't do volume. The space of volume. Let's call it volume for sure. You get something you can compute for. That's the pressure. The pressure. But this pressure is just you get the pressure, which is the compression of the pressure. But it's not really good enough. Which it doesn't tell you. In order to bring it doesn't tell you the impression. You don't tell you this is the problem here. This is the real problem here. The real problem is you get a volume here, but the volume is the x-axis. So the pressure is the power. Volume is the power. Sorry. So you get access to power. This is power. P for power or PSI power. The power of the system is literally just the power to the key, so the power to the volume, but the volume is a compression, so it gives noise. It's noisy. So why is it matters? Because it's noisy. So volume is not static. It's a dimension, and that dimension is noisy. And noise can be noisy. That's what the problem. That's what really matters. The problem is. So when you get pressure, when you get something that that applies a force. And that force is a piston force, and it goes in increments. It goes from 0.25, 1,000 kg divided by 4. I'm trying to do it. 1,000 divided by 5. No, divided by 10. Divided by 10, 100. That would be 10. So this would be 100 units. No, this would be 1,000. But 100 divided by 10 again. Divided by 5. We'll do 5. That would be 2. 1,000 divided by 10 to 15. Let's do 15. Because let's do 100,000 divided by 10. Basically, 1,000 divided by 100. Because I'm thinking about basically go 100 divided by 1,000. But you usually do model. You guys usually do the model. So the number 0 or 1,000 or kg is literally just the same thing as it goes in tens. So that'll be more easy to compute. So this is a pressure. This is a piston pressure compression. We can't really measure the opposite axis of this because you have to flip the dimension. You have to just flip the dimension. I'm sure you guys here. You have to flip the dimension. You have to so you have to take a picture. You have to change your coordinate system. You have to flip the whole dimension. You know what I'm saying? That's what it matters. You have to flip it. I'm not going to serious. So that's how it works. So you get the x-axis and get the y-axis. So for example, get the 1,000 kg on the x-axis, and that will be the what we call the pressure of the power pressure. Now the power of the power pressure is because of the power piston. It's a piston, and this piston will be so you actually measure if you're measuring x squared plus y squared equals r squared, where r is 0.5, where r is 0.5, you get one and one, which you get the full dimension of this x axis. But this dimension has the so on graphic opposite of the system. So you get so when r reaches is what minus 5, get minus 5 squared. This will be minus 5 squared will be x squared minus y squared equals minus 5. Because you work in the inverse axis. So this is why I'm saying it matters to me. Basically minus 5. So basically back to the system. So you get the system here, but there's two. You have to flip something. You have to rotate it in two directions. You have to reorient it. So this one must you have to reorient it. So we're back to state one. So this is like so you have two axes of x, y. XY, this is plus x plus y, and that'll be 0.5, 0.5. This is 0.5, this will be this axis of pressure. Pressure will be piston pressure. That'll be piston. That'll be piston. This will be the piston pressure, but this is the axis. We get the opposite axis, which like there'll be the opposite one. So this is like a more of noisy area. This one basically, if you imagine this is a piston, this is power, 2 over what over. Wait, this is power. Power X. This will be a piston volume. This will be what the volume that it gets. Because if you get pressure, you get noise. So this noise is what you get a measure, but it's noise that's data. It's kind of noise. Basically, if this is space here, if the volume dissipates, it doesn't go into nothing. It goes into our system, and that is what is happening in the pressure system. So in the pressure system, so you get a kind of inverse joint. Because if the pressure is void, that means the weight. So it's kind of a content switch. So you get half and half. So half plus half, basically, you get 5. This is like a 1,000 kilograms. Now you get minus 1,000 kilograms. But if you flip the dimensions, you're looking at 1,000. Basically, you get 1,000 kilograms, but that's shared between 500 milligrams of the weight. And that's what really happening here. So you get x squared plus y squared equals r squared, and get s squared minus y squared equals minus 0.5 minus r squared and that'll be pi r squared resistance. So you can complete that interval in space and time via the resolution framework, via buoyancy. Now, buoyancy is very important to understand because everything is buoyant. So if it's buoyant, because this is like I think it's like water. If you don't understand what I'm saying, this is buoyancy effect. So if you drop like something that can float in water, think of it. Buoyancy just affects let me try and mention it. So buoyancy, if you have a medium of water or liquid medium, and you put some kind of a ball in some kind of bouncy ball, what's it called? So it's buoyant, that makes it start flow, but you push with force. It will this is like a liquid water, this is like an ocean. So this is what I'm saying. If you don't understand what's happening, this is how you calculate it. So this ocean is the noise, but it's not noise, it's like because it's in the medium, and that's what this kind of thing is like doing. So it's in the middle. So if you drop something like some kind of missile in there, and it has some kind of beach missile, you have to sink it first. So if it takes half the time in one medium, it takes half and half the time in a more dense medium, and that'll be how the system works. So if you have 0.5, you have 0.5 to the power of 1, but that'll be 0.5 power of negative 1. So it's negative 1 and negative plus 1 is what is 1 negative 1 and 1. Depending on how you look at it, but get half of the half is dense. You get 0.5 to the power of I didn't do that. So get 0.5 to the power of 4, and that'll be basically this 1 million times to the power of 2. So you get 0.5 to the power of 2. So if it's 0.5 to the power of 2, this is 0.25. So basically, when something has a force, it ends as 0.25. 0.25 is just the force is what? The force is what? If the medium slows it down, has the friction of force equals mass acceleration. Net force equals 0. Net force equals 0, and energy equals mass acceleration. If the mass is what 500 or 1,000 500 kilograms, 500 kilograms of something that's buoyant like water, uh, displaces the force and basically it's buoyant because the basically say you join like some kind of large something that's floating like some kind of water something that goes in water and buoyant can flow some kind of so you try to see a duck. But the duck was like a rubber duck. It's a big rubber duck. You dump down a good one from a height of like height 7 feet, 9 feet, 10 feet, 10 feet, 10 feet, 10 feet, 10 feet. So get 10 feet, 10 feet. Let's do it height. It's 10 feet. A rubber duck, a big rubber duck. Let's say how many grams? 500 kilograms over 10 feet. That would be 0.5 kilograms per second. But you got gravity. Gravity is just the dimension that models that sees everything, that glues everything. It's just it has to equalize the glue. So this is just one dimension of space and time. And this means you get out 500 divided by 500 divided by what? Divided by 10. Wait, not 100. 10. So sorry, 500 because 500 divided by 10 is what? 50. 50 kg. Not 0.5. It's 50 kg. Because that's you get 50 kg of force at a time. This is like a interval decision. So you get 50 kg at a time per second. Per second. But this second is not a G. So get 9 you get per second. This is just the calculus. So graphs will be how to hold. This is because this time the graph will really hard in the left board. But it doesn't stop there. Basically the left one was like a gravity model. So I'm thinking left is a gravity body. They work on the axis of gravity. We got the mu ones. The mu ones is basically it means is hold the mu ones hold the left ones and the left ones doing the hold us, which is gravity. But the mu ones are half of half. So that'll be half of it. So that'll be but if you drop this on a new one, if you drop this on a new one, a new field, a quantum muon field, you get it to the power of 4. That'll be like so if the gravity is 500 degrees on Earth, 100 degrees and we drop it at divided by 10, 10 kg, 10 milliseconds, 10 seconds. 10 feet. So this will be the feet. Now the feet is just the feet, but no, this is not time. This is the feet, this is the height in feet. So 10 feet will be 0.5 feet per second. But if you get this to be 4, basically if this was 10 feet, this would be gravity model of what 50 kg. But this will be in the muon world of 100. So this stuff will be automatically 100 because you get 8 times by 100. You get 10 times 10. Basically it's stable. Basically means like 10 basically has double the mass of it. So you get half million. If this is half million, 500 kg to the power or divided by 10 is what? 50. 50 feet. 50 feet. Now, 50 feet is just gravity. Now, if you get 50 feet divided by 10 again, will give you what? 100. So this will be a 5 feet. So the we take 5 feet, 5 feet for something with that a muon to something that's a left. It takes 5 feet for this system to get some. So you get 10 feet, 10 feet. So 10 feet. So you double this one. So 10 feet is just a standard model, but in this medium, we just double it. So basically, this half is like the half feet. So this 10 feet, just 10 feet of drop. Now, if you do the 10 to the power of 2, it will be 100 feet. 100 feet is 100 feet. Now, 100 feet is now the state of the water. So you have to cut it by half. It's actually the ratios are half, but this is water. The water slows things down because it's more dense, really packed. I don't know the nuance of it. Basically, they hold things for longer, better. They hold things forever, indefinitely, because they hold hold this because they hold the state already. Basically, this is like a compression. So you see, if you compress something, you already have a medium volume, and that volume is so dense you can't compress it more. But so it slows down more. I'm saying so it slows down more because it's so compressed. Because it's so much more. Whether gas or liquid doesn't matter. It slows down more. You don't pump it. You compress. You have to compress that space to get more space. Which is a vacuum problem. So you get 500 now divided by 10. So 500 kg divided by 100 is what? Kg is what? 5 kg. Now 5 kg is like this weighs 5 kg in water. If you are in that medium, but that medium is not good enough. Basically, this medium is a polar axis. It's a polar axis. So 5 kg is just one medium of the system. So this is what if this is liquid water, if this is an ocean is densely packed, you get like a solid liquid gas. So this is like this one's water. So this top one's gas, and the other one this is water. If you drop from water, if you drop from water, the Boyle's law of the rate factor will just double. So you have to try to reorientate your angle basically the speed. Basically that's what the road doesn't really matter. Because you have to travel on something, some kind of space. The road is there to slow you down or slow you down safely. Basically, the when you measure the road, you measure one over the fraction. This fraction is one over the system, but this one for basically, you have to basically now basically, this one over is like get measurement. You don't get fully everything. And this is saying to you guys, you don't get fully everything because you are measuring with the wrong tool. You're measuring with the wrong units. You're measuring with the wrong dimension. Basically, you're measuring the wrong dimensions. And then you're measuring wrong with the wrong, not wrong tools, wrong dimensions. Example, you get the Boy's law, you get the Lorentz factor, which is doing the measurement itself. This is actually measuring so you get the measurement of the self, measure of the system. So you get the measurement here. For example, this is like the light speed. But this is x to prime, but this is like the Gaussian transformation. I don't really know. What you're saying is like you're measuring until dimension behind because you don't really if you do the static Lorentz transform, it has to evolve with the growth of the system. Based on its movement, based on what so it's like a thinking the system, dimension. It's like you have to tell a point if you either if you don't enter the right, if you don't if you enter a dimension that's a far, if you keep going faster near light speed, you're entering dimensions. You can teleport. Basically you can start teleporting because you can just that's why I see this is something you can really just teleport the dimension because you are really in one dimension of light. And light can allow you to teleport. But if you're going to light speed, there's no point of really just having that speed forever. You just have to start teleporting. You have to start using other properties of quantum physics. You're quantum lattice. You're in a quantum lattice, which is dimensionless, which is dimension, which means you are getting dimensionless. You're not losing dimensions, you're getting more dimensions, but you're not actually measuring dimensions. That's why you're not actually like measuring dimensions using the Lorentz factor. And that's the problem is, for example, this is like 1 over square root of I. If this is one dimension, you get a half or square root of I of the dimension via minus the volume of the constant time, the constant slice speed. If you go like this speed with the this is what I was to say. One dimension is like this 1 unit over the third of the dimension. This is like the signal you're processing. The third. Now this third is what? The third is -1. So square root of -1 is what? Square root of 1 is what? -1? Yes, -1. So you one of what is this? Sorry. Oh, I didn't know. Yes, so sorry. Sorry, 1 second. So you get the square root of 1 over -1. Oh, that's okay. So just like square root of 1 over -1. Now so you have to come there. It's like the more dimensions you enter, you get the left hand and get the most. Now the one that has the 100 is the twa, the T for tango, A for alpha, U for umbrella. So that gets the 100. That gets everything of nothing. That measures nothing to be honest. The twa is like the measure of absolute nothing. It wants to be nothing, but it's not absolutely nothing. It's like if I'm going so far, do I prefer stability or just becoming nothing? Given a mass, but if you measure twa, you are in a state of equilibrium. Basically, you're teleporting. You have just transcended. You're just basically you're moving to if you're in the light speed, you're teleporting. But if you're at 12 speed, you're getting so this 10 units, 10 times 10, 10 units, 10 kilograms, no, 50 kilos, isn't it? This if you're driving from 10, if you're flying from 10 feet, basically if you're flying, let me just see where you're gonna be. 50 to the power of 100. Okay, let's say 50 times 10 times 10 times you get 210 feet, 10 to the power of 3. 10 to the power of 3 is what? 1,000. 10 to the power of 3 is 1,000. 1,000 kg. And that's really because you're a third dimension of axis. Basically you're working on 3 axes. That's what the tour is. Basically they work on meters. So basically, if you can move in this world physically, you're weighted by gravity, which is what the left hand. You're in the Neptunian world. You're bound by Neptunian gravity, which I like to call it. And if you get the more M for Mike, U for umbrella, O for Oscar, you're bound by what? The physics of the space-time curvature over the British space. It's like being in space, but you are moving at the speed the speed any observer literally asks. That's what you gotta be. That's what. Sorry. Basically, I'm gonna go up now. Don't worry. Basically, that's the lowest factor. Literally, what you gonna do. So basically, the twa is the equilibrium. But the mu1, basically is the dimension above, below it, and that's where the compression starts happening. Doesn't matter how far you go, you have to use a twa to go to teleport, to start teleport. You have to be between the more speed. So you can get the more speed by plugging this function in. So remember, if you have a weight, if your ship has a weight of 1,000 kg or let's say 500, 1,000 kg, which is the maximum, and you're going at light speed. What's light speed? The light speed, one mostly, I'm going to try to work this out. Light speed. Simply, you know what I'm saying? So you have to like distill the pressure. You don't distill, you have to switch the dimensions you're in to get the right tools. So, if you're measuring the wrong system, if you're using the wrong system, basically it's a time series graph. If you're doing the wrong derivatives at the wrong time, if you basically when you switch the derivative, wait, how do I do this from? How do I give it? Okay, let me just give me this formula. Give me a problem using two sets of potential differential equations for this given 1,000 kg and into 500 into potential differential equation for pressure and time using pressure and velocity in Lorentz points. So let me just solve this problem. Let's see whether they can give me a problem I can solve. I don't think I'll solve this problem, but I'll see what I can do. You will not give me a problem. You will not give me a problem. I swear, I won't give me a problem. If it doesn't give me a problem, I don't really want to tackle it. But I know it's like a problem for me if I don't tackle it. Let me just try this way for it. Bernoulli principle. You're not asking me a good question. I know it can give me a question, but I just want to ask you what can give me a question. Thank you. So e to the power of I squared plus so equals plus 1. Just so I get plus 1. So problem statement. So let's try this from if I first do like obviously the mass is 1,000 kg. 1,000 kg a cube. Let me try to get this properly. I know I'm doing, but let me see properly. I'm gonna go up now. This is going up properly. It's not really I'm to see it properly because like I'm gonna see my face. Like it's gonna annoy me. So I'm gonna see my face. I don't see anything that's about my face. It's from basically a problem. Upper mass is 1,000 kg. 1,000 kg. It's a cube of silent L0 equals 1 meters. Rest frame. Just the rest frame is just the still state. It flows at a neutrality of a fluid psi. That's psi. P equals 12 kilometers per divided by meters cubed. Or rest density. Basically just the volume. That's basically this is what I'm saying. So basically, object of mass m is a cube. Cube is a dimension, has a dimension as a volume. So it's a volume. So immediately, I already know it's the derivative of the direction. So I just know that the derivative. You have to do it over time, but I know at least the derivative of the two levels. So I have to divide two equations here. But I'm dividing. Sorry, I'm doing properly. I'm doing wrongly. So I'm going to. So the mass is 1,000 kg. So this is like paper. I don't really need. I keep like messing up. All right, I'm really unhappy with that. Because this is what I'm saying. It annoys me literally. It annoys me because I'm not doing it the way I want to. So the mass of a cube equals 1,000. That's equals silence L. Mass of a cube is m. And then the silence is what? Silence is L0 equals 1 meter. 1 meter. So 1 meter does be L3. That's L3. That's L3 equals Ln equals is a set of L to Ln equals n to the power of m. That would be cubed. And as well, basically I'm saying rest frame of 1. It flows neutrally in the density phi equals 12,000 kilometers the rest density. So the rest density, where both rest the object set horizontal because the 0.8 is constant. Obviously, 0.8 is just everything travel time. For these dimensions are by launch factor. Due to the dimensions along the direction of motion are reduced to launch factor. Perpendicular motion remains unchanged. That's a right angle motion. Perpendicular, this is a right angle. But perpendicular, no. This is perpendicular, no. right angle, no, parallel, yes. Assume dimensions are incorporeal to density and change 9.8 meters per second is gravity. Constant time is 3 and then times 10. Notice what calculates 5 for every 0.8 basically you get to one of the number one is just the volume. So if you have the volume, that's just the volume or the maximum density they will share. That'll be one. So this is you get two functions, one of volume, I mean one volume of dimension. So phi is 0.5 second, but that's what the last one for things is. So let's call the dimension. Dimension D, the level is one. The first one got comes one dimension, which is the one right dimension. One basically one right dimension is two left dimensions, one right. So this one left dimension, this will be sorry, this will be somewhere L. But this one left, this is one left, this is like a one left, but this half or this was to or half or one left dimension. This left dimension is like a phi, but this phi is one, but this one is like a XYZ. So you get like dimensions are perpendicular to it, and now a B phi. So you get a dimension L0, L11, L to the power of 3. So the summing dimension is to the power of 3. So you get dimensions left 3. So you have the left 3, L0. So you get L0, L3. L to the power of 3 is dimensions for density left. That'll be phi, 0.8 seconds. But this is a Russian. I don't really want to think about this. We can get the trace to get one level, but do this over time. So the pressure of this is what? Basically, I'm trying to give you the kind of transformation you need. So this one guidance solution, this is like a guidance solution. So you can solve them. I did like to solve it for me. Basically, it solved it for me. I'm not really happy it solved it for me. I don't really wanna. This ultimate zero, this is L0 to 3, 1 to 3 squared. This like it solved it for me. I hate the solution really. It's just like the fluid rest space is like the buoyancy effect. It's like the buoyant force of the force 0 B is P compute FB in moving cube is moving cube. So basically, the buoyancy force is the dimension force, the kind of thing that in one dimension. But you know, the twa is what the maximum dimension can go to, and that's what the twa is. It's like measure of nothing. But that nothing is the entire dimension of measurement. It's like you get 1,000 and you get one. You get one. And the difference of between 1,000 divided by 1, 10. You get basically you share a shade of 10%, 10% of growth factor. So you get 10%, 10% is the growth factor. So you get 1,000 kilograms divided by what? One times which is one dimension of space and time. And what times the kilograms per second per no psi. Let's try and calculate that. 1,000 psi per for every 30 seconds. Because you know you don't have to every half second every half. So you have to half everything in space and time. So every half second, let me try to do a question here. Get 1,000 psi. Let's try to think about this problem. So basically 1,000 psi. This will be 1,000 psi calculator. So basically you have a state of a half of everything. So basically you get a value. So everything, so we say that everything 1,000 kg share half in density, and that density is the volume. So you have a half of the volume. So everything is just be halved to get a chemical state. So you have to half everything. 1,000 divided by 2 is 500 kilograms. But 500 kilograms is just if you have 500 kilograms, you get 1,000 divided by 2 is 500 kilograms. But you have to share 250. So you get two halves of 1,000 kg divided by 2 is what? Obviously, this is a rubbish PSI calculator. I really had one open, I just lost it. I just didn't know I could literally. Basically, it's like a 1,000. It's like a boat's diameter. This like pressure. The boat's diameter is what? 5. So get a 1,000, 10. So get a burst of the diameter is just 10, but you know you get 5, but you get the diameter, but you get double. You use it in pi, so you get pi r squared. This is pi r squared, but you get pi r squared 2 pi r. 2 pi r. So the share half of it reverses. So you get to half the time, the speed. So you have 10,000 kilograms of mass, and you get what 5,000. 5,000. No, 1,000 divided by 10. They share 10% of everything because they evolve together. That will give 1,000 by 10 is 100. 100, but 100 plus 100 plus 100 kg of space and time is the pressure. That will be piston pressure. 1,000 kg. This is module kg. Kilonewtons are basically this is a piston force in newtons, but I don't see the kg. Basically, what I need kilonewtons are basically 10 kilonewtons. 100 kilonewtons is what 100 kilonewtons is like 1,000 kilonewtons is like 5, and that would be psi. 100 kilonewtons bare meters. So piston 1,000 1,000 one. If the piston force is 1,000, and the diameter is 10, that means there's a trade-off, and basically you get the bore area of bore area is like the full area. So make it the I'm just writing it down properly now. So you go to calculate that's it. So everything if the 100 is different is in the state of state, you get 1,000 divided by 10, which is the bore diameter, which is 5.5. Because the diameter is 10, you need to be 1 to 10. But you get 10% of a steady state, which one measures that's 10 is shared. And that'll be one shared state that's 10% you can share because it's stable. It's stable, it's not 5%, literally. But 10% of this kind of pressure is what on the bar cylinder pressure. But cylinder pressure is like the pounds per square inch. This one means like pounds per square inch of psi is psi of cylinder pressure, which is like the pressure in a cylinder, from a cylinder, on a cylinder, because it's pressure onto a system. It's 1,060, but this is pressure where you don't want to put your hand like that under the cylinder. So basically, on the cylinder was going to compress, and the bore edge is like 8.54, and the bore diameter is 10. So basically, that's the stable. And we get this kind of physics, we get some kind of calculator. So it's like the pressure one. But we don't calculate, I won't calculate the kind of space, the kind of temperature, but it's temperature calculate like a pressure. Temperature. So let me see. Calculate. Try to get temperature. Oh no. So get a temperature. Temperature at sea level. Basically, you get this kind of so you get the same thing. In artificial, you get basically you get this on axis. What does that mean? So the 10 units are in axis. So the 10 plus 10. So to get you get so this 10% is wrong. It's not really right. So this is a dimension of time. So this is 10,000 psi, but this is just one axis of dimension. So you have to get the thing cut off at some kind of unit. So do you take the derivative of this kind of system? The pi 360 is one polar rotation left. We need two polars, which is like a 360 by 360, which is 720. So this is two. I think what I mean by two axes. You have to get the constant time of two axes. That means you have to get the third derivative of the left axis. Basically, you have to get two left rotation. That'll be 362 times 2, which will be 360 times 2 as well. 360 times 2. Which will be 720. So you have to rotate 20 to get one right pole axis. Basically, if you're going at the speed and you exceed something that has the pressure, that's the speed, the speed or the pressure in any dimension you're in, and if you use polar coordinate system, that is no contagion. On the lattice, you get 720, and that's two left, full resolution. Basically, you have to now start measuring the opposite of the Lorentz factor because you can't get any information from the you have to use the same Lorentz factor, which I'm supposed to do to get the same information. Because if you get f prime, you have to find the derivative of prime, the third derivative which is prime, which is called the jerk. Now the jerk is like a jerk of which is a constant jerk. So it can be 18 milliseconds. For example, let's say it's 18 milliseconds. Let's just say it's 18 milliseconds. Let's go because I don't really want to do this kind of thing. So you have the pressure and the time. There's still some kind of solution. Oh, I'll go something here. Can I No, let me go this now. Let me just stop this now. Let me just try auto save. Let me start again because I'm gonna do one more thing. I'm just Basically, you got a derivative, place and pressure. Matrix via Boyer's theorem. This is basically just like a little, just like, oh no, it's like a open file location. Well, give me 1 second. I'm almost done. Okay, I promise you. So I just like got like it's good for me to like do this for myself because that's my work I do. Sorry, when I do because I love this work. It's like I've been in computer. Well, I love to do computer because I just try to do it myself. But you know, I still go to I still get time to go next year, but not Cambridge this time. Somewhere else.
Done, right? It's already 10:30.
Yeah, I just I'm almost done, Wally. That's what I'm saying. It's like oh, basically get a copy here and get a copy here too. But you get the polar axis copy with a polyfilm. Boy, yes, you get this thing. So literally, I got to do this right now because it's like a. Did I stop this thing? No, I didn't stop it. No, it's not stop this. It's like it. Basically, I have to stop this boil system. So really, let me try to give it to Claude or something because you know Claude can eat it up. DeepSeek, there's like a Claude Kimi. DeepSeek what? There's like a Lexicon. Oh, there's like a little oh, there's like a. Come on, literally. Almost done. Only just like a little, just take your time. So basically, I have to like a little just try to do it now. It's now or never. It's now or never. Let's just do it now. Basically, get my go-to single here. ODTS. So this is my example here. It has to be done. It has to be done. So basically, we continue from the other way. This is just I'm in the GitHub repository. Same date is 29th of December 25. Basically, you get the example of this. You get a jug. Some people call this jug. So you get the first derivative of 9 sub, but this is the one dimension of space and time. One full dimension. Obviously, this so you get the first derivative and second derivative. But this is like it's like a constant time. So it's like a per second. So you get per second. This like per second, 18 milliseconds, 18 minutes per second per second. But it's just arbitrary number. It's not arbitrary. It's just it's control. So you have to divide. If you want the dimension, you have to divide it by 3. Because 3 you have to do the dimension. You can do 3. That would be 18 divided by 3. Calculator because they share 3 dimensions. So basically they share they have x, y, z, which can be pressure or volume. So you get 3 dimensions, you get 66. So if the x, y, z is 3, 2 divided by 2 is 6. So they share 6 properties, C6 properties, because they share 3 dimensions. And that's 3 divided by 3. So this shared 2 is the C6 property. So C6 canonical state or calculus on equilibrium. You can think of them as just some dimensions that own something. They get 6 divided by 6 to 3. So you now get 2 axes. So yeah, see, think of it like a prime function tree. So 18 divided by 6, 6 is 3. 3 is 6. You get 3 axes. So you cannot get 3 and 2 one dimension space that share space to 3, and that'll be 1 and 3. In the share between 1 and 3, just like a 1 and 3 marker. So you get 2 dimensions, 1 for every 1 dimension is 3. For every one dimension, there's 3 shared properties. They have when you divide 18 by 3, 18 by 3, you get 6. 18 by 6, you get 3. 2 by 3, divided by 3, you get 6. Or 3. If you divide by 6, you get 3, and that's the left root, right. So if you get 18, you get 6, and that's 6. 6 what? 6 properties. 6 shared states. Calculate tomography. Tomography, which is the area measurement. So this is like a way you can use for relation. So for every 6 tomography dependency hierarchy pressure, like, if it's pressure, really, the more pressure you, if this is pressure, this is a pressure time graph, a pressure space graph, really. Basically, you get the dimensions, but you get 6. Why not divided by 4? 18 divided by 4. That'd be, let's try that actually. 18 divided by 4, I don't know. That's really 18 divided by 4.5, because it's not kind of come. 18 divided by 6, 5 as well. I don't really want to think about this problem, but the kind of 6 times 3 is 18. You know what I'm saying? Because you have to do x, y, x, z axis, the share. But I'm thinking of the problem in the kind of way but this is like you get half the problems in 2 solutions. So you have half the problems in 1 solution, and that the share 3 dimensions. So the kind of thing you see is 6 divided by 3 is 2. I think divided by 2 is 2. So you get 3 plus 3 plus 3, you get 6. But the shared 3, that means 3 plus 3 is a half. The shared a half, a ratio of a half problems in the model, which are states. You have to think about states. You don't get, so basically, this is just the channels sharing 1 problem into the machine, because that's what we have 3 doors. So you have right root. So again, if you want to get 8 on the root, 6 on the left root, and the left right root you get 2, on the left right you get 3. I get 3 on the left right root. I get 3 on the right left root. I get 1 on the right root. Of the AVL tree, of the server, of the GC tree. But the shared 3 and the 3 are in the sixth dimension, which is the axis of the top down. Basically, the first basically the second the second leaf node, the share the share what half, the share half. So usually 3 times 2 is 6, the share half is something. But in the third root, the share half, because 3 times 2 is 6, and 6 divided by a half. Really, so a half of 6 is what? The 3. The share a half in that dimension. Basically the share half coefficient with everything. But if you get to the last root, what is this share? Basically, you can if you get to half, you get some function of half, you can do this. Half times 3, half of what? Half of 1. 6 to 1 is 3 to 1 as well. A third. So you have a third of something. A third times a half. A third times a half is what? A third plus a half. A third plus a half is 1/5. 1/5. Third plus a half is what? 2, 3, 4, 5, 5, 6, 7, 8. 5, 6, 7, 8. 5, 6, 7, 8. 8. 5, 6, 7, 8. 8. It's not fair on me, man. Anyway, but I don't really know. But I'm saying it's demographically. It's like it was a kind of way. You have to find how dimensions align or polarity align. Basically, kind of because you get 3 and 2 in one dimension. 6 to 2 is 3 and 2, and that's what 1 and 6. Based on how you want to do it. But dimensionalizes. But you get some dimensionalizes there. So 2 times 2 is 6. 2 is 6. But this sort of GCD can come up with to give you 18 is because if 1 is meters, you can have an interval 1 over meters, which is secant. For example, let's do it properly. So get the secant. So get the number 6 and 3. The number divided by 3 because 3 dimensions. So 18 divided by 3 is what? 6. But this 2, so you get the secant of what? If you get the secant of what? The secant. The secant is what? Rise of ram. So you get the so ka toa which is y over x over z. But the cosecant is x over y. So you get x over y, which is the not 1 over x. We get 1 over x is just basically the one above it is just all of the calculus. But the y over x is just the first derivative of that step. You gotta take. Because it's just basically you get 1 over cosine x, but that's gonna measure nothing. Because that's the basically that's basically x. Basically we can get one. Sorry, we can get one. We can get 1 over. We can get 1 over sine x, which is like which is like a 1 over x y of x. But that's just basically the unit non-state. But this is not good enough for measuring dimension. So you have to get let's just try it actually with the Fourier series graph. For to get Fourier series. This is like a matrix form. With Fourier series. Fourier series. Oh. So basically, this is a Fourier graph. Let me try to do it properly. So this is a Fourier graph. So basically, I'm going to try to do one of the. So this is 10 is stable. So you get sine x, but you get 1 times the n is number of increments. So you get n is just 1, but you get divided n. So you get so we get 18. 18 is what? 18 dimensions 18 meters per second. 18 divided by 3 is what? So you get 1 over sine x. Sine will be opposite of 100. So that'll be sine n times x, n times x, n times x, basically, this is just the y over x. This will be SOHCAHTOA. Y over x will be a cosine x, so x over times 2 times n. But this is the 1 over n. So this is the kind of unit, but this is like a 2 noises. So you get 1 over the whole system, 1 over the kind of system here. But this is like a dimension. So this is like a 1 dimension of it. So you have to do 3 of it. 3 divided by 1 over. Yeah. But this is 3. I'll just give you 1 dimensions of it. Because 1 over this kind of 1, this is like 1 looking at. So this is sine x over cosine. This is like y over x of the units. But the dimension is the interval of 1 unit. But this 1 unit is like the sine 3 divided by a sine n over sine of cosine x. And this x times n. But this 1 dimension of it. The unit is just 1. But if you get 100, you're measuring opposite. So this is just a y matrix. You get the system there, but systems that is traced by the system. So you get some kind of an area, tomography area. But this was incremental on the other end of pressure. So if you have this for each dimension is 3 units, and that's what represent the kind of row structure with the inverse units of this. So if you get 3 divided by xyz, you get the shear half is state. But you get 3, the shear half of something. So if you have this one divided by 3, that means you share divided by 1. This is just 1. The full units of 1 over 1 but you get the negative 1 here to get a negative 1, negative 3. So basically, you have to you take this function and you flip it. So how you so basically you rotate it. Basically, you have this function. You see this function. This function you can't really observe. And you have to get the transpose of it, and that's what I'm trying to do. So you have to get a transpose for a matrix. So I'm trying to do it differently. How do you transpose for a matrix? Transpose. You get the transpose of this. You get the sign thing. Transpose for a matrix is like let me search you get this function. Transpose of a matrix. Transpose. Like the transpose is like the transpose of a matrix here. Basically, I can do some paper. Let me try to do a paper. Basically, I'm going to try to do a paper because this one is my answer. I don't want to fuck it up on the calculator. So you get 3 over divided by so basically this is sine n times x n times x which is n is a natural number, but divided by cosine x times n. But that's basically 3 divided by all of it. 3 divided by all of the system. But this is, you get the matrix here. But this is the same matrix of sine n times x cosine x times n to the power of negative 3. Because this is just a unit matrix. This would be like a 3 polar rotations. But you transform this apply some transformation 3 times. So for this to be work, you have to compute the inverse of it once. The inverse of this sine, the one sine to the power of 1. So you get the integration to twice or 3 times. Because it's minus 3, it's minus, you have to rotate the equation 2 times. We use the open differential function. But the dimension of this is like 2. So you have to reach the dimension. If you are computing the dimension of -3 number, so you get -3. So you get the derivative. So you get the area. So you get -3 to 1. So it's minus b minus 2. You become 1. Sine n times x. This sine x will be divided by 3. It will be 3. But this time it's 3 to the power of 3. -2, because you have to get an error. You have to we take the inclusion, you have to get times and divide by value, times the power, okay, divided by the power and times the value. So divided by the power, divided by 3, sine x x times x divided by to the power of -3, divided by power is like sine over 3, and then take away divided by, and then times divided by the power, times by the power, divided by the power, and then add 1, times by the power, add 1, subtract 1, divide and then subtract 1. So that'll be -2. So that'll be sine n times x to the power of -2 so divided by 3 minus the power of -2. Now this is a new one. You have to now compute division over extensively. Sine divided by 3 will be what? Basically, you have to get we have to compute this one. This is one step of it. This is one topographic area. So now sine n times 3 x divided by 3 will be x divided by 3 will be 1 because you have to calculate the equation. So you have to do with sine. If we take sine, you're going to anti-clockwise. So this will go anti-clockwise. You go. It doesn't matter what you do now. You can't fuck it up. Basically, let me try and mix the video properly. So this will be sine, which is sine will be yn. So this will be y equals sine n times 3 divided by minus 2 divided by 3. Anyway, so this is like divided by 3. So you get sine x. So you basically get divided by 3. That'll be sine 3 sine n. Because you have to times by 3. Times by 3. So you get 3 times n, and then x times x will be 3x times 3x. So it's just one equation of a negative -2. -2 is like the same thing. So you now get -2, then get tan divided by 2, and you have to divide by 2, and that'll be 6 sine n to the power of 3 times 2 is 4. Because 3 n will be n plus because you have to times by n. 3 plus n to the power of 5 plus 3n 3x plus 5x. Now 5x to the power of 1 is divided by 1 is what the power 1 is 3. You have to get one more derivative of it, or one of integration of it. Times, so if you divide, you multiply, divide, you add. So 5 to the power, so you get to -4, you get -1, and get sine 6 sine 5 plus 1 is 6, because you get 5 plus 2. N to the power of 5 plus 6, 5 plus 1 is 6. So you get 6 here, and then plus 6 times 1 is 5x, and that'll be 5x, and that'll be 3n. So this is 6 sine n, n to the power of 6 plus 5x. That's what it says. It's like same thing I'm saying. So this is the first thing I've done. It's like this is like the what I've got. But this is just one step, 1/10 of a step. No, 100, because I started with 1,000 kilos. No, this is the 10th step, the O's chair. This will be the chemical state of a muon. But gets basically this will be over something else. This will usually be over cosine. But same for the cosine. Cosine x times m will be if I to the power of 3 will be divided by 3. It will be 3 cosine divided times 3 cosine 3x times 3m 3 cosine, and then get the next one will be negative 2 6 cosine 6x times 6n next one, and that'll be 6 cosine 6x times 6n. This was zero. So you can get the four. I see this is the two equations you get. This is the first one I did. And this is the second one I did. So this one you get now get what? A shared state of this guy. I'm not sure it properly to you now, but I'm sure it very poorly because I got to show it to you, no one else. It's my work. It's like a little bit annoying because it's spitting on paper. It's like a so I got this kind of work I did. So it's multiplication. These are dimensions of inverse dimensions. So this we can measure in that dimension. You have to start looking at this kind of axis. This is what you got. See, this rotation, this axis rotated. This axis rotated because it's like the axis you now have to get information, the same information you are because you're moving so fast. In the muon field, in the muon quantum lattice, because you get the electron, which is the kind of air we orbit, and the space we all have in space, and we get that's what the muons are. I'm guessing that's why we move faster than light speed, and that's what I'm saying. What the black holes are, and those get So basically, this is x-axis, so cosine what? Sine cosine. So this is sine cosine. This is like so x plus n. So we should get 6 sine n to the power of 6 6 plus n to the power of 6 plus 5n plus 6n plus 6n plus n. No, plus 6m. No, plus 6m. This was 6 to the power of 6 over the cosine one, which is 6 cosine over 6x plus times 6m. This is what I'm saying. That's the answer to this solution. This is just one solution of the system. It's just you will take to get the muon. This is 10% of the growth factor that everything has in the basically we live in the 100%. We get 1%, but if you go to you don't get 100% here. If you are the field left out, which is how you get 10% less of everything. So you have to go to get the muon field, which is in space. So you can measure muons in space. That's what I'm saying. The muons are just 10% stable because there's no gravity there in the sparse structure. But this answer here is not good enough. Because I want to go to sleep, I gotta do it properly. So this one the muons, if we get the 100 units, we can get faster than light when you are in the Twa mode, and that's like at the 100 stability. You can really get the maximum speed for the dimension measurement of space and time. This dimension represents the pressure you're putting on the field around you and the field against you, but you can divert the pressure to the engine. Because you have a push, you now have a different quantum field you're working with. Because you enter a different dimension of pressure. That's what I'm saying. That's what really saying. That's what the whole thing's method is. But I got to think about the lattice. I can't remember the question I said in mind. What's the question? What the question? So basically, what I'm saying, we start at 18 here. So basically, this is the 18 question. We're not getting this kind of 6 sine in brackets n to the power of 6 plus 6 times x to the power of 6 or 5. X power x plus 6m 6x plus m. Then divided by cosine 6m plus 6m. Cosine 6 cosine divided by 6 x sine plus 6. As I'm saying, it's meant to be stable there. It's meant to be working as intended. Into question. I can't remember the area. The area that topography. You got a map. Okay, I'm going to go to sleep now. I'm going to touch it. So I remember what I'm saying. It's not what I'm saying. I can't remember what I'm saying. I can't remember. There's no kiwi here in my head. Thank guys. Thank you for watching. Thank you for have a lovely day. Thank you, Nami, guys. It's not working, guys. Guys, do it properly. You can't do it. No doing properly. I'm doing like a room chat. But it's not working on me. It's like a shoe in my work sign. opportunity of a project. Like if they were, I love my black face. I love my I'm so handsome. I don't really want to show you, but you know, just show you too. I really want to show you that. Thank you. That's it. So I'm going to the NTS.